Universal Time.
I am in radio contact.
Okay, so today on the bench we have the True Time by Kinemetrics, model 468 DC, satellite-controlled clock. Now when I say satellite-controlled, these units actually received a signal transmitted from the NOAA GOES satellites to set the time. There was time code information that was provided by the National Bureau of Standards, later the National Institute of Standards and Technology. In 2005, I believe it was, the time code quit being updated by NIST, so these clocks basically fell silent. So today we'll be taking a look at this one because we have some sort of issue with the power supply circuit in that it's causing the unit to randomly reset. And then also we'll be taking a look at a modification that converts it from GOES satellite signals to GPS satellite. So quick overview of the unit. Back here we have the incoming RF processing board, which takes a 5 megahertz signal from the antenna, which I do not have one of the right antennas, but the right antenna actually takes the 468 megahertz, down converts it to a 5 megahertz IF, which this board then translates to a digital signal that this board here then uses. So this is the signal processing board, and then it gives its signals to this unit, which is the microcomputer of the clock. And then over here we have the power supply section. So this power supply is interesting in that it makes 5 volts for the logic circuits, a couple of different voltages. I think it's -6, +12, +5, and then also there is a high voltage circuit, because one of the things that makes these clocks interesting is that the digital displays that are in here are actually Panaplex, so they need like 180 volts to run. Okay, so looking at the schematic real quick, down here in the corner we have some sort of +5 A and B monitoring circuit, which is going into a comparator NPN transistor and then feeding our reset switch on the main board. But what's really odd about this is it looks like it's capacitively coupled. So not really sure what's wrong with that, but we'll take a look. Okay, we got +5 there, looks good. Nothing on that one. A little off of +12. Got -12. We got -5. So I'll have to look at the schematic, but I'm thinking that point should be another +5, but have to check and make sure. One of the things you can do when looking at a power supply also is set your meter to the AC position and then go back and look for your ripple. So hardly any ripple on +5. There's ripple on that one. That could also be a no connection. Hardly any ripple on, I think that was plus 12. Hardly any ripple there. Hardly any ripple there as well. So that tells me these capacitors are actually in pretty good shape. Okay. So this is our 180 volt test point for the Panoplex displays, and that's doing good. Move the meter a little bit so I can get at some caps that are down here. Looks like that's ground. 12. 4.62. And falling. So I sort of think we might have a bad 7805. What do we got over here? That's ground. Minus 12 over there. So that is, well, got another cap over here to take a look at. 5.0 on that one, but 4.6 over there. Okay. Okay, so the voltage regulators are actually mounted on this metal bar, and they're put on with like Molex connectors, so it actually makes changing them fairly easy. So one moment while I change those. Pull them out like so. Pay attention to which way they go in the socket. You will need this information later. Actually in there pretty tight. Okay. Okay, so now we can measure our regulators outside of the board. So on these regulators, it's input, ground, and output. The tab is also at ground. So with a negative voltage regulator, that's actually different, so don't let that bite you. When in doubt, look at your data sheet. Figure out which is in, which is out, because it is different on a negative voltage regulator. Okay, so here we got 13.37 in. For some reason we're seeing 10 out. Unless these have, I'll have to look it up. These are LM2940, so maybe they have a different pinout? Okay, so quick sanity check just to make sure our test equipment's functioning right. I have one of the replacement 7805s that I'm going to use. It's actually a L7805CV. And on my output, I measure 4.99, just like it should be. 13.38 in, 4.99 out. Okay. So for some reason, these parts, when I measure them, well, there I get 9.3 out. So now it's 10.9. Definitely bizarro. Do not know what's going on with the original regulators that were in here. Okay. We'll drop a little dab of heat sink grease on the back of these rigs. Just a little dab will do ya. You don't need to go overboard with this stuff. You're just trying to fill microscopic gaps. And I'll get these screwed back in. Smoke test. No smoke. Good. One of the regulators reads 4.93 and 4.87 on the other one. So hopefully that calms down our reset issue. Okay, so moving on to our modification to make this receive GPS time code instead of GOES time code. So we want to remove this board here, which is the 5 megahertz to digital converter. So I've already unscrewed it. And then we just pop it out with the ribbon cable here. And then what I have designed is this board here, which it has an AT-Tiny 1614 and some associated circuitry, which will take a GPS module, take the time code, convert it, and give it to the unit in a format that the unit actually wants to see. So here's what a completed module looks like. So it mounts in the original position. Have a couple of 3.5 millimeter jacks in here for one's to program the GPS module and the others for diagnostic purposes. And it can also be used to program the AT-Tiny 1614. So a special shout out goes to Andrew Novick, who was really boss, and he was able to find me this. So this document actually has the post-1984 time code for the GOES satellite. Let's see if we can find it here. So you'll see versions of this in various documents that deal with the GOES time code. But none of them that you can find online were updated with the extended bits here, the format edition. Why we want the format edition is because a couple of the bits, it's either this position or I think it's actually the stat position, where those bits indicate daylight saving time. So because of Andrew coming through, I was able to program the code that is in the time code converter to actually work with daylight saving time. Because in this unit, this switch here actually controls whether you're looking at daylight saving time or not. The switch above it forces a normal time versus 24-hour time, which there's no indicator whether it's AM or PM when you're in that mode. And then these two switches here are to compensate in microseconds for like how far you theoretically are from the GOES satellite. So I disassembled it so you get a good look at a completed unit. So this is the GPS programming header. This is the microcontrol serial diagnostics and UPDI programming header, depending on how you have this solder jumper set. Basically just line up our mounting post like so. And screw her down. Okay, plug these in. Make sure red goes all the way to the right when facing the unit. So that's our +5 input. And now we add a SMB to SMA little adapter cable. So this is a 2-inch one. In the future, when I do this, I'll probably want to use like a 6-inch one and then loop it around just so I don't have this much of a bend on the coax here. And I am also using a couple of, I believe these are 1032 fender washers to act as a spacer through the original antenna mounting hole. And yes, I work on top of a trash can. Okay. And I'll find a little wrench or something to tighten that up. Alright, we'll add a GPS antenna. There is a jumper on the board that selects between 3.3 and 5 volt GPS antenna power. I currently have it on 5 volt. And turn it on and see how long it takes us to get something. Okay, with the unit back on, our colons have gone solid, which indicates that the clock is receiving valid time code from our GPS to GOES converter board. The clock will also give an indication indicating which satellite it believes it's receiving the time code from. So it just lit the west indicator. So I have it fixed in the code that it's receiving time code from GOES West at 133 degrees longitude. So hopefully here in a bit we'll get valid time code on the display. Alright, and there we have it. Alright, so now we're successfully decoding the time coming from the GPS to GOES converter. We are at day 295, 14 hours, 29 minutes, and 50 seconds. I'd like to give a big shout out to Paul Swede, WB8TSL. He was the one that originally came up with this project, and I'd also like to give a shout out again to Andrew Novick of the National Institute of Standards and Technology. Without both of them, this project wouldn't have been possible.